And finally, in the last two parts of the lecture, I'd like to step back and consider two potential applications of ER equals EPR. In part three, I'll review Maldacene and Susskind's original proposal that ER equals EPR provides a solution to the firewall problem in the context of the black hole information loss paradox. And then in the last part, I'd like to consider the extent to which ER equals EPR might provide a causal explanation of entanglement correlations. First part, entanglement entropy versus minimal area cross-section of a wormhole. So again, there are two claims here. First general claim is that entanglement entropy is the appropriate measure of entanglement that corresponds under ER equals EPR to minimal area cross-section of a wormhole, on the other hand. And then there are these two additional claims. Both of these measures are conserved under quote unquote local operations, and both satisfy a monogamy constraint. And again, the implication is perhaps they measure the same thing. Right? Maybe these similarities are evidence for the ER equals EPR hypothesis. In a previous lecture, right, we were already introduced or reminded of the notion of entanglement entropy as a measure of entanglement. So for a bipartite system characterized by a density operator state, rho sub AB, the entanglement entropy S sub A of subsystem A is given by minus the trace of the reduced density operator with respect to A times its log, right? Where the reduced density operator with respect to A is obtained from the composite density operator state by tracing out the degrees of freedom with respect to the other subsystem. So that's the proposal for a measure of entanglement. Now, what about minimal area cross-section as a measure for what we might call wormhole conductivity? And one way to motivate this measure for wormholes comes from the RT formula that we discussed a couple of days ago. Right, so the RT formula is a statement in the ADS-CFT correspondence, and it's associated with the constructions in these diagrams on the right. Right, so we're asked to consider a space-like surface that goes completely through the bulk, and where it intersects the boundary, let's divide that boundary space-like surface into two subregions, R and its complement. Then with respect to R, we can define this bulk surface gamma sub R, the minimal area bulk surface associated with R, in terms of these three properties. So gamma sub R has the same boundary as R. The union of R and gamma sub R forms the boundary of another bulk surface, call it H sub R, referred to as the homology surface. And finally, gamma sub R extremizes the area functional. Right? And the RT formula says, well, the entanglement entropy of a boundary subsystem with support on R can be calculated in terms of the area of the corresponding minimal area bulk surface gamma sub R divided by 4 times G, the Newtonian gravitational constant. Right? This was the original presentation of the RT formula. Now, let's focus on the specific example in which the bulk spacetime is a wormhole spacetime, perhaps ADS Schwarzschild, extended ADS Schwarzschild spacetime, right? And furthermore, in that case, let's also specialize to the case where our boundary spatial subregion R consists of one of the two boundaries of a bulk spatial slice, a spatial slice of a bulk wormhole spacetime. So in the diagram at the bottom, this, recall this paraboloid of revolution, this is supposed to represent, right, a spatial slice of the bulk. And it has two boundaries, and we're assuming one of them is given by R and the other is given by the complement of R. In this particular setup, we can still identify a minimal area bulk surface, gamma R, associated with R. But in this case, so the argument is to uphold condition B of the RT formula, our gamma sub R in this case must be a cross section of the spatial slice. Right? And remember, we've identified spatial slices as kind of wormholes at an instant, right? And that's because, right, according to condition B, the union of gamma sub R and R must form the boundary of a completely enclosed bulk surface. And if gamma sub R is not a cross section of the wormhole here, then there'll be a part, the union of gamma R and R will not form a closed boundary of some bulk surface. So to uphold B, in this particular case, gamma sub R must be a cross section of the spatial slice. And to uphold C, right, it must be the minimal area cross section. Right. So the RT formula suggests, to summarize, the RT formula suggests that if we have adopted entanglement entropy as our measure of entanglement, then the corresponding measure of a wormhole should be given by the minimal area cross section of the wormhole. Okay, so we now have a measure of entanglement, and motivated by the RT formula, we have a measure of what we might call wormhole conductivity. And now we can assess these two claims, right? That these two measures are similar. And the first claim is that they're similar in the sense that both are conserved under local operations. In fact, this was one initial observation made by Maldacena and Susskind in their original article, right? And this is an attempt to make that observation more rigorous, as I understand it. So the conservation under local operations with respect to entanglement entropy is fairly straightforward. So let's call this conservation of entanglement entropy, claim 1A. Let AB be a bipartite system in a pure state, rho AB, that acts on some product Hilbert space HA cross HB. Then the entanglement entropy of subsystem A, the claim is invariant under transformations that take the form of, let's call it a bipartite operator, product operator, UA cross UB, where UA and UB are unitary operators that act on individually on the two factor spaces. Now, this notion of local operations as encoded in, right, operators of this type, this kind of product operator, arguably it's a notion of local in the sense that this product operator, the action of it on the composite system consists of separate actions on the two subsystems, right? UA acts non-trivially only on degrees of freedom associated with subsystem A, and UB acts non-trivially only on degrees of freedom associated with subsystem B. And this seems to be a separability understanding of the notion of locality associated with the term local operation. And the only point here is that the separability understanding of locality is distinct from a localizability understanding of locality. Right? So the idea here is that the product operator UA cross UB can act in this separable way on subsystems A and B, even when the subsystems may not be localized to, in the sense of having support on contractible regions of space. Right? The subsystems A and B could be sort of globally extended systems, right? And we can still define the action of this separable operator on them. So it seems like the separability notion of locality can be made distinct from a localizability notion of locality. And it's the separability notion that seems relevant to this claim of conservation of entanglement entropy. All right, so that's the claim that entanglement entropy is conserved under local operations. So what is the dual claim about minimal area cross-section for wormholes. And this appears in an article by Rimmon and colleagues from 2016. And the theorem they prove is a bit more complicated than the theorem on the previous slide, insofar as they attempt to prove a theorem for a generalization of the minimal area cross-section of a single wormhole to apply to the general case in which we have a collection of some indefinite number of wormholes that potentially are interacting with each other and other forms of matter. So it's supposed to be a generalization of minimal area cross-section to the case for multiple dynamic wormholes. And so what I would want to do now is just simply report on the candidate that they choose ultimately to represent this generalization of minimal area cross-section. So their setup involves a multi-wormhole spacetime and with these three features. So they assume that it is asymptotically ADS, that it is globally hyperbolic. It can be foliated by a family of Cauchy surfaces, and that it satisfies this condition in general relativity called the null curvature condition. And moreover, it's a multi-wormhole spacetime insofar as it contains some number of wormholes, each joining a left and right horizon, such that we can identify a region that consists of the union of all the left horizons and a region that consists of the union of all the right horizons. And finally, it's past initialized in the sense that they assume that for some time t less than or equal to 0, say, all the wormholes are far apart, except for maybe one. And this is just, I think this is just a simplifying assumption that lets them view the space-time region for t less than or equal to 0 as extended ADS Schwarzschild spacetime. So within this spacetime, they then identify the following constructions. So they first identify a space-like foliation of M, of space-like surfaces gamma parameterized by T. For a given member of this family, they then identify the intersection of that member with the union of all the left horizons, call that L sub T. And similarly for the intersection of a member with the union of all the right horizons, call that R sub T. Having identified LT and RT, they then identify the causal diamond anchored at LT and RT, which they call W sub T. So think of W sub T as the domain of dependence of a space-like surface that ends at LT and RT. And now they focus on a given causal diamond so defined. In particular, they identify a family of space-like slices of a given causal diamond indexed by some parameter alpha. And within that family, for each spatial slice, they identify a minimal area cross-section, call that C sub T alpha. And then they step back and say, let's now define what they call C sub T as the maximal such minimal area cross-section for a given family of slices. And this C sub T then is their candidate for the generalization of minimal area cross-section for a single static wormhole to this more general case of multiple dynamic wormholes. So maybe to make these constructions slightly more concrete, here I reproduced a diagram from their article on the right here. This is supposed to be a conformal diagram that represents the ith wormhole in this collection of wormholes. In particular, where it intersects various these constructions on the left, right? So LTI and RTI are the intersections of the ith wormhole with these LT and RT regions, right? Then WTI, this green wedge region, is supposed to be represents the where the ith wormhole intersects the causal diamond WT associated with LT and RT. And then the family of spatial slices of WT are represented by these green lines, right? These green curves that join our LTI and RTI. Right? They represent spatial slices. And for each spatial slice, we identify the minimal area cross-section of it, and that's represented by these dots, these green dots. So we have a collection of these green dots, and then we identify the maximal cross-section in this collection. And that's their candidate for the minimal area cross-section associated with all these wormholes. And in this diagram, B sub I is the bifurcation surface associated with the ith wormhole. The point on the space-like surface sigma sub 0. So this is their candidate for the minimal area cross-section for this very general case of a multi-wormhole spacetime. And it's the subject of the theorem that they then prove. So call this conservation of minimal area cross-section. Right? And this is supposed to be the dual to the conservation of entanglement entropy theorem on the previous slide. So the statement is as follows: for the family of spacetime regions WT defined as the causal diamonds anchored on the piecewise connected outermost apparent horizons, LT and RT for an arbitrary set of dynamical past initialized wormholes and black holes satisfying the null curvature condition, the corresponding maximum surface, right, their candidate for the minimal area cross-section, divide into left and right collections of wormholes, has an area that's independent of T, equal in the sum of the areas of the initial bifurcation surfaces of the wormholes linking the left and right sets of horizons. And as I understand it, roughly the proof involves showing that this CT surface is upper bounded by the sum of all the areas of the bifurcation surfaces associated with the wormholes. And it's this part of the proof that requires this technical condition, the null curvature condition in general relativity. And then the second part of the proof is to show that CT is lower bounded by the same sum. In any event, right, from a conceptual point of view, Riemann and colleagues interpret their theorem in the following way. And I think this is what ultimately is important in determining the sense in which this theorem is dual to conservation of entanglement entropy. So they make the following statements, quote, thus the maximum surface, right, it's the CT surface, divided one collection of wormhole mouths from another, has an area that is conserved under arbitrary space-time evolution and horizon mergers, as well as arbitrary addition of matter satisfying the null energy condition. This is a statement in general relativity, quote, that is a precise analog of the statement of conservation of entanglement, unquote. And furthermore, their theorem, claim 1b, is the gravitational dual of entanglement conservation, and thus constitutes an explicit characterization of the ER equals EPR duality in the classical limit. Now, I take it so this is their interpretation of their theorem, right? And their interpretation seems to be making at least two claims. And the first is that the time independence of the CT surface that they prove is interpreted as an invariance under classical time evolution, right? And that seems a reasonable claim, given the assumption of global hyperbolicity of the space-time, and that indicates that, right, a given causal diamond encodes all possible dynamics that might govern time evolution of matter fields off of any one of its spatial slices. Now, the second part of the second claim that their view of the theorem seems to be making is the following: this local time evolution on the ER side, right, associated with their theorem, is the dual of local unitary evolution on the EPR side, right? That's the sense of local operations underlying conservation of entanglement entropy. And there seem to be two concerns associated with this second claim. The first is kind of naive, right? Unitary evolution is more general than time evolution, right? Time evolution can be associated with unitary evolution when the evolution operator is a Hamiltonian. So it seems as if the first claim about conservation of entanglement entropy is broader in this sense than the second claim about conservation of minimal area cross-section. And minimally, that indicates that these two theorems should not be thought of as dual to each other. Yeah. If they're dual, then there can't be a sense in which one is broader than the other. And the second concern is just a concern over possible conflation of two different senses of locality in the term local operation, right? So in the first claim, local operations are local in, as I argued, a separability sense, which in principle is distinct from a localizability sense of locality. Whereas in the second claim, local operations do seem to be local in this localizability sense. Right, local operations in the second claim really amount to dynamical evolution, right, of a localized system from one initial data slice to another, as opposed to a separability notion of locality. So it looks like by local operations are meant in two different ways in the context of these two theorems. So right, while the similarities between these two theorems is suggestive of a possible link between entanglement and wormhole connectivity, I would suggest that the similarities are not conclusive of such a duality. All right, so that's one claim that has appeared in the literature, right? About a similarity between entanglement on the one hand and wormhole connectivity on the other. Another claim that has appeared fairly recently is that both of these measures satisfy a monogamy constraint. Right? So the monogamy constraint is fairly easy to state in the entanglement context. So here's one way of stating what we might call entanglement monogamy. For a tripartite system, A, B, C, the amount of entanglement between A and B plus the amount between A and C must be less than or equal to the amount between A and BC, where E is some entanglement measure. And so if we assume a fixed amount of entanglement between A and BC on the right-hand side, then we get the following two claims. The greater the entanglement between A and B, the less between A and C. And when A and B are maximally entangled, right, when they exhaust all the possible amount of entanglement, then A and C cannot be entangled. Now, assumedly, right, the ER equals EPR dual would be something like the following. Let's call it wormhole monogamy. In this context, the claim would be for spatiotemporal regions, A, B, C. The following inequality should hold, right? The amount of wormhole connectivity between A and B plus that between A and C should be less than or equal to the amount of wormhole connectivity between A and BC, right, where W is a measure of wormhole connectivity. So for a fixed amount of wormhole connectivity on the right, then we have the correlates of EM1 and EM2 for entanglement, right? The greater the wormhole connectivity between A and B, the less between A and C. And if A and B are connected by a maximal wormhole that exhausts the available wormhole connectivity, then A and C cannot be connected by a wormhole. So now there are two questions now, right? The first is, can we formulate an expression for monogamy in this general sense, specifically that involves entanglement entropy? And that's naively, that's a non-trivial question insofar as entanglement monogamy is defined with respect to a tripartite system. And we've been considering entanglement entropy up till now as simply referring as a measure of entanglement for a bipartite system. So is there a way of extending the concept of entanglement entropy in such a way that we can impose this monogamy constraint on it? And if the answer to one is yes, then the subsequent question is, does the resultant expression hold for minimal error cross section of a wormhole? Now, one has been answered in a positive way by appealing to a particular configuration of entanglement entropies called the mutual information of a bipartite system. And it's this quantity of mutual information that then we can impose a monogamy constraint on. Right? So the mutual information for a bipartite system AB is, call it IAB, is defined to be the entanglement entropy of subsystem A plus that of subsystem B minus that of the composite system AB. So intuitively, it's the difference between the amount of entanglement of the two subsystems and the amount associated with the composite system. And we can now directly impose the monogamy constraint on mutual information, right? IAB plus IAC should be less than or equal to IABC. And if we substitute in the definition of mutual information in these three cases, we get this inequality, right, for the corresponding entanglement entropies. So call this the well, this is the monogamy constraint on mutual information expressed in terms of entanglement entropies. Now it turns out that minimal area surfaces in the RT formula satisfy this inequality. And this was demonstrated by Hayden and colleagues in this article in 2013. So here's their cartoon proof of this claim. So let's focus on the left diagram. The horizontal line is supposed to represent a region of the boundary of a boundary spatial slice. And it's further decomposed into three subregions, A, B, and C. And the curves that extend downwards represent bulk surfaces with that are anchored on the boundary, right? In particular, we can identify the minimal area bulk surface gamma AB as that bulk surface with the same boundary as the union of A and B that has the minimal area, right? So that would be this surface in the bulk that has that ends at the left endpoint of A and at the right endpoint of B, right? So part of it is in this diagram, part of it is purple and the other part is red. So that's gamma AB. Gamma BC, right, is the minimal area bulk surface with the same boundary as B union C. So that would be this surface, right? The first part of it is purple, the last part of it is red. And similarly, gamma AC is the minimal area bulk surface with the same boundary as the union of A and C. In this case, the A and C are disjoint, right? So the subregion that is their union is the union of two disjoint regions. So we might expect that the minimal area surface corresponding to this boundary subregion also consists of the union of two disjoint surfaces, right? So gamma AC is going to consist of this bulk surface, right? The thin blue surface union this bulk surface, this thin blue surface, smaller one, right? That's anchored at the endpoints of B. And then we can take this to some of the areas of these three minimal area surfaces. So that's the quantity on the left, right? And then the claim now is the result we get should be equal to the area of the following surfaces, the expression on the right, where, for instance, gamma sub A tilde is a bulk surface that has the same boundary as A, but is not necessarily the minimal area bulk surface with that property. Right? So it's represented by this fat purple surface, right, that has the same boundary as A. Similarly, gamma C tilde is a bulk surface that has the same boundary as C, but not necessarily the minimal area such surface, right? And it's represented by this fat red surface. And then the last term consists of the area of gamma A, B, C, which is this. That's a minimal area bulk surface with the same boundary as A union B union C. So that's this thin blue bulk surface, and gamma B is the thin blue bulk surface with the same boundary as B. So the total area of the sum of the areas of the surfaces on the right should be exactly equal to the sum of the areas of the surfaces on the left. All we've done is we've sort of reconfigured the surfaces, the bulk surfaces on the left, in a slightly different way. Right? We haven't added or subtracted any bulk surfaces and moved it from the left side of the equality to the right side. And then Hayden and colleagues note that, well, the area of gamma A tilde, it must be greater than or equal to the area of the minimal area bulk surface gamma A with the same boundary as A, right? And on the figure on the right, that's represented by this thin purple surface. And similarly, the area of gamma C tilde, right, this fat red surface on the left, is greater than or equal to the area of gamma C, the thin red surface on the right, under the assumption that gamma C is the minimal area surface with the same endpoints as C. Gamma C tilde is just another bulk surface with the same endpoints, not necessarily the minimal area one. And so that justifies the inequality expressed in the second line here. And we've now reproduced, right, the monogamy constraint for entanglement entropy now in the form of area of minimal area bulk surfaces that appear in the RT formula. Okay, does that make sense? So Hayden and colleagues claim this particular monogamy constraint for entanglement entropy is imitated by minimal area surfaces in the RT formula. In retrospect, it seems to be a short step to a similar claim about minimal area cross sections of wormholes. Right? So an appropriate combination of minimal area cross sections of an appropriate wormhole configuration also satisfies this inequality. And in retrospect, that shouldn't be all that surprising, given that, right, the RT formula was an initial motivation for adopted minimal area cross section as a measure of wormhole connectivity. But the proof for minimal area cross sections of a wormhole was demonstrated by this article by Garibian and Pena in 2014. So call this monogamy of mutual information for wormholes. The claim is that for a multi-throat wormhole that connects regions A, B, C with each other, and with any other region D, right, we reproduce this inequality that characterizes monogamy of mutual information. And the proof, or at least the cartoon proof, is just follows the same methodology as the cartoon proof for the minimal area surfaces in the RT formula. Right, we express the minimal area cross sections of the wormholes in this particular configuration on the left, and then we kind of reconfigure them into non-minimal area cross sections in an appropriate way, and that ultimately establishes this inequality. So to step back, right, Garibian and Pena claim, make the similar claim, right? Entanglement entropy and cross-sectional area of a wormhole have this additional similar characteristic feature, and so far as appropriate combinations of them can be shown to be constrained by monogamy. So perhaps they're measures of the same thing. Now, with respect to this claim, there are a couple of concerns that we might voice. The first is a general concern about the constraint of monogamy. Is monogamy an essential characteristic of entanglement? And it turns out not all proposed measures of entanglement are monogamous. I mean, on the other hand, we might, if we're advocates of ER equals EPR, might take this just to indicate that the duality embodied in ER equals EPR is for a particular type of entanglement, right? Namely, that type that does satisfy a monogamy constraint. Now, another potential concern is just how to interpret mutual information in the context of wormholes, right? So the mutual information associated with two regions A, B connected by a wormhole, assumably takes this form. The difference between the sum of the sizes of the two individual throats associated with regions A and B and the size of the joint throat that connects AB with any other region, right? That would be this cross-sectional area, sigma AB. And this doesn't seem to be a measure of connectivity in an absolute sense. At best, it's sort of a measure of relative connectivity, right? And moreover, right, this also suggests, raises the question, should the ER equals EPR duality be restricted to pure bipartite entangled states and correspond in bi-throated wormholes, right? Given that entanglement entropy was originally introduced, or at least is best understood as applying to bipartite systems. So for a pure composite state, rho AB, the von Neumann entropy of it is 0, and assumingly that under ER equals EPR, that entails the area of the minimal area cross section AB is 0. In other words, right, there is no third region that A and B are connected to. So A and B correspond in regions A and B are in this case connected by a bi-throated wormhole. So I guess the concern here is just that if we take ER equals EPR to be a statement about bipartite systems and correspondingly two regions connected by a wormhole, then this similarity in terms of monogamy isn't going to be applicable. So again, right, the similarity is suggestive, but not conclusive of a duality relation. All right, so those are two claims, right, in the literature that suggest these two proposed measures of entanglement on the one hand and wormhole connectivity on the other have similarities, but then the question is, are those similarities enough to establish a duality? And arguably, at this point, that's probably not the case. So let's now move on to the second part of the lecture. Let's now change the subject slightly from similarities between measures of entanglement and wormhole connectivity to similarities between constraints on entanglement and wormhole connectivity. And at least three similarities between these sorts of constraints have appeared in the literature. So I'm going to refer to these as no-go theorems. One is similarity between the no-Siglin theorem involved in entangled states and the non-traversability of ER wormholes. Then the second is an implication of the no-clonin theorem for certain entangled states on the one hand, and implications of the no topology change theorem in general relativity on the other hand. And then the last of these no-go theorems involves an alleged similarity between the non-detectability of entanglement on the one hand and the non-detectability of wormholes on the other. No signaling versus non-traversability. And this similarity was originally discussed in Maldacene and Susskind's original article. So on the EPR side, we have this no signaling theorem. So here's one way of stating it. For a bipartite system in a pure state associated with this product Hilbert space, the reduced density operator rho sub A for subsystem A is invariant under transformations of this form, IA cross UB, where IA is the identity on HA and UB is a unitary operator that acts on the Hilbert space for subsystem B. And the intuition here is that the statistics that govern measurement outcomes on subsystem A are encoded in the reduced density operator rho sub A. And the claim indicates that local operations on subsystem B have no effect on the reduced density operator rho sub A. So a consequence then is if a superluminal signal is a signal that exceeds the speed of light with respect to an inertial frame, then entanglement correlations cannot be used to send superluminal signals. Just by performing measurements on our subsystem A, we can't determine if somebody has performed a measurement on subsystem B over there. So that's no signaling in the context of entanglement. Now, Maldacene and Susskind suggest that this no signaling corresponds to the non-traversability of wormholes, right? So they ask, can a wormhole be used to send superluminal signals? And the case of interest seems to be the following setup, right? So our two regions in the previous claim, we have two regions X and Y in a wormhole space-time. And we have two ways of connecting them, right? In the exterior part of the space-time and through the wormhole, right? And the case of interest is when X and Y are space-like separated in the exterior region of the space-time, right? The only curve that connects them in the exterior, the only types of curves that connect them in the exterior are space-like. And in this setup, the question of interest is, can they be connected by a causal curve that goes through the wormhole? And the answer to this is no. Any future directed curve that passes through a wormhole must become space-like along some of its extent. And that's demonstrated by, for instance, the conformal diagram of extended ADS Schwarzschild spacetime, right? In this case, we can think of region X as a subregion of the region 1 and region and Y as a subregion of region 4, right? And the claim is any curve that connects the two regions, right, that intersects the event horizon at some point along its trajectory has to become space-like. Right, so that's the non-traversability of wormholes claim. Right, does that make sense? And again, so Maldacene and Susskind suggest this claim about wormholes is the dual of the no-signaling theorem for entanglement. But we should be aware of the following disanalogies between these two claims. One point to make is that it turns out a wormhole can be made traversable, whereas an entanglement correlation cannot be made to send superluminal signals. Right. So the idea is there's a necessary condition for wormhole traversability, and this was described in this article by Morris and colleagues in 1988. So the necessary condition is a violation of what's called the average null energy condition in general relativity, where the integral is over the stress energy tensor TAB and contracted with a null curve in. So roughly this says there is more positive than negative energy along any null curve little n. And if this condition is violated, then Morris and colleagues showed that we can come up with a scenario in which two regions, space-like separated in the exterior, can be connected by a causal curve through the wormhole. So that's one disanalogy, right? And another is seems to be the following. It turns out both the no-signaling theorem and the conservation of entanglement entropy claim from a couple slides ago are both consequences of the following general claim. Under an arbitrary separable operation UA cross UB on a pure state of a bipartite system, the reduced density operator for one of the subsystems has a particular transforms in a particular way, right? And it's this transformation characteristic of the reduced density operator that ultimately entails both the no-signaling theorem and the conservation of entanglement entropy claim. The point here, though, is that there's no analogous claim that underwrites both non-traversability and conservation of minimal error cross-section theorems on the ER side. So in other words, right, no-signaling and conservation of entanglement entropy seem more connected than their correlates, their wormhole correlates appear to be. All right, so that's one example of no-go theorems that have been claimed to be dual and provide evidence for ER equals EPR. And here's another example. This is no cloning versus no topology change. And this is described in another article by Bain and colleagues from 2015. So their claim here is the following. The no cloning theorem and the topology conservation theorem in general relativity are in fact dual no-go theorems under ER equals EPR. So the no cloning theorem is the following statement. There is no linear unitary operator U that acts on two qubits, say, in this particular way, right? The second qubit is in the zero state. The first qubit is some unknown qubit. And the action of U just duplicates the unknown qubit in the second qubit. So that's the no cloning theorem. The no topology change theorem that Bain and colleagues are referring to here takes this form. So this goes back to papers by Tipler and Board. So again, this is a theorem in general relativity. So it says, let M be a compact region of a spacetime that satisfies the Einstein equations with space-like boundaries, sigma 1 and sigma 2, if the average null energy condition from the previous slide and this other condition called the generic condition hold in M, then the two space-like boundaries are diffeomorphic and the entire region M is just the product of a copy of sigma and the interval 0 to 1. And that's an indication that there's no topology change, that it has throughout M, there's a constant topology. So the generic condition, the fine print is, it's given by this technical condition on the curvature tensor. And it's one way of interpreting it is the following. It encodes a non-zero tidal force at any given point. So the no topology change roughly schematically can be represented by the following conditional, right? If the average null energy condition and the generic condition hold in a space-time M satisfying that has these features, then there's no topology change in M. Now, the strategy of Bao and colleagues in this article now is the following. They demonstrate the following two claims. First, a violation of no cloning for certain entangled states entails superluminal signaling. And then they show, similarly, a violation of no topology change for a wormhole spacetime entails superluminal signaling. Right? So that's supposed to be the connection between these two no-go theorems, one associated with entanglement, the other associated with wormholes. So let's consider these two claims in the yellow box at the bottom here. So the first is, let's call it superluminal signaling via entangled states and cloning. So here's a method for sending superluminal signals using entangled states if we have access to cloning, right? If the no cloning theorem is can be violated. So for two subsystems A and B, if two subsystems A and B comprise a bipartite system in an entangled state, and B is repeatedly cloned, such that the following two conditions hold: each B clone remains entangled with A and unentangled with the other clones, and B, if the entanglement between A and any B clone is broken, the entanglement between A and the others remains intact, then the claim is a superluminal signal can be sent from A to B. Now, the task for superluminal signaling in the context of entangled states is to determine if a measurement outcome at B was due to a measurement outcome at A, right? And the no signaling theorem says that we cannot accomplish this task because simply by performing a measurement at B, we can't determine whether or not a measurement was performed at A. But the claim now is if Bob at B has clones, then he can measure them sequentially, and that allows him to determine whether or not a measurement was made at A. In particular, the same result would indicate that a measurement was made at A. And these two conditions are necessary for this procedure insofar as condition A guarantees that a measurement of A influences all clones in the same way. And condition B guarantees that a same result at B is not due to a measurement of a prior B clone. So here's maybe one way of making these two conditions a bit more explicit. So the idea here is that the rather complicated tripartite entangled state on the left, the phi state, is an entangled state that satisfies these two conditions A and B, and thus if we interpret two of the subsystems as clones, it allows for superluminal signaling, whereas the tripartite entangled state on the right does not satisfy A and B, and it cannot be used to send a superluminal signal. Right? So probably the easiest way to see that phi satisfies A and B is to consider the analogous entangled three-link, right, under Aravan's analogy. Right? So the claim is that here is a three-link in which the A circle is entangled with the two B circles. Think of the two B circles as clones in a way that satisfies A and B. Right? Each of B1 and B2 is entangled with A, but not entangled with the other B. And if we break the entanglement between A and one of the two B's, if we cut one of the two B's, then that preserves the entanglement between A and the other B. And that's the phi state is supposed to be the analogous quantum entangled state. If we measure, say, the B2 clone, A remains in an entangled state with the B1 clone, and the two B clones are entangled with A, but not with themselves, not with each other. And on the example on the right, the corresponding 3-link is, well, it's the Borromean rings 3-link, right? And the corresponding entangled state is the GHC state. So in this case, this is a case in which condition A is violated, right? The two B circles are not entangled with the A circle, right? If you consider the B2 circle with respect to the A circle, the B2 circle is kind of on top of the A circle, and similarly for the B1 circle is beneath the A circle. And if the entanglement between A and any B clone is broken, the entanglement between the two Bs is broken too. So this is a entangled state that doesn't satisfy conditions A and B. Okay, so that's an implication of no clonin, a violation of no clonin and entanglement, right? It raises the possibility of superluminal signaling. And the dual to this, according to this article, is superluminal signaling via wormholes and topology change. So the claim is if the no topology change theorem is violated, it similarly produces a scenario in which we can send superluminal signals. So let M be a compact region that has space-like boundaries, satisfies the generic condition, and contains two disjoint regions, A, B, connected by a wormhole. If M undergoes topology change, then the wormhole can be made traversable and used to send superluminal signals. And this is essentially a consequence of the no topology change theorem in sort of its contrapositive form, right? So the no topology change theorem is the statement, if there's topology change in M, then either the average null energy condition is violated in M, or the generic condition is violated in M. And so if we assume the generic condition, that entails the average null energy condition is violated, and that's an ingredient in transforming a non-traversable wormhole into a traversable wormhole. So again, right, we have seemingly two similarities between the consequences of two no-go theorems, one in the context of entanglement and the other in the context of wormholes. So here are some concerns we might raise with this similarity. Well, first, it's not really a similarity, a duality. It isn't meant to underwrite a duality between cloning and topology change in general, right? It's a similarity between consequences of cloning and consequences of topology change. And moreover, the second claim for B is more general than the claim involved in entanglement, insofar as entanglement in general is not sufficient for superluminal signaling via cloning, right? It's a particular type of entangled state that satisfies these two conditions that allows for superluminal signaling. And there doesn't seem to be that type of constraint in the corresponding theorem and the wormhole context. Right? And more generally, no cloning in the entanglement context is underwritten, well, in the context of quantum mechanics in general, is underwritten by linearity of observables. the proof of no clonin requires the assumption that U is a linear operator, it turns out. Whereas no topology change seems to be dependent on contingent features of the spacetime, in particular, right? These two conditions. Okay, so again, there are disanalogies associated with this proposal of this type of evidence for ER equals EPR. All right, and the final example of a proposed similarity between no-go theorems in the entanglement and wormhole context involves non-detectability. And this is described in an article by Bain and colleagues from 2015. So their claim here is that the non-detectability of entanglement is dual to a non-detectability of wormholes. So here's the statement about non-detectability associated with entanglement. The claim divides into two parts. The first is that there is no observable can determine if a system is in an unknown entangled state, but there is an observable that can determine if a system is in a known entangled state. So with respect to the first claim, right, suppose there is an observable PE that projects any vector in a multipartite Hilbert space onto the set of entangled vectors in the space. Linearity requires that PE answers, say, yes to two vectors. If it answers yes to two vectors separately, it should answer yes to their sum, right? If it says vector A and vector B are entangled, then it should say the sum of vectors A and B are entangled. But the point now is that the sum of two entangled vectors may not be an entangled vector. So that's the sense in which no observable can determine if a system is in an unknown state, entangled state. But the second part of the claim is, right, there is an observable that could determine if a system is in a known entangled state. And the idea here is fairly simple, right? Suppose we know that the phi state is entangled. Then there's a way of determining whether any other state is entangled in the same way. We just project it onto the subspace spanned by phi. Right? We use this the projection operator associated with our known entangled vector state. So that's the sense of non-detectability of entanglement that Bain et al. Refer to. And now their claim is there's an analogous sense of non-detectability in the wormhole context. So let's call this non-detectability of wormholes. So their claim here is, again, it's this two-part claim. First, no local observable can determine if a black hole is in an unknown wormhole state, in particular, whether it's a one-sided wormhole or a two-sided wormhole. But two, there is a local operator that can determine if a black hole is in a known wormhole state. And by that, they mean if it's of a particular two-sided type with respect to a particular way of categorizing two-sided wormhole states. So let's consider the first claim. So their idea is the following. So here's their distinction between a one-sided black hole and a two-sided black hole, right? So a one-sided black hole is a black hole that's been produced by the gravitational collapse of some amount of matter. Right? And here's a conformal diagram in which the world line of the collapse in matter is given by this diagonal. A two-sided black hole, sometimes called an eternal black hole, it's the case of for instance, it's represented by the conformal diagram, for instance, for extended ADS Schwarzschild in its full glory. And it's two-sided in the sense that two observables in the two exterior regions, 1 and 4, can jump through what they take to be two different black holes and yet meet in the middle, potentially meet in the middle. So the first claim is, in this context, reduces to the claim that there's no local observable that would let you determine whether you're in a region, an external region in the vicinity of the event horizon of a one-sided black hole, or whether you're in the corresponding region of the event horizon of a two-sided black hole. So that's, in other words, right, the region in the vicinity of the event horizon in the left diagram is identical to the region in the right diagram. So that's the basis of their first claim. With respect to the second claim, there is a local observable that can determine if a black hole is in a known wormhole state. Their idea is the following. First, here's a procedure that would allow two observers to determine if they're in a two-sided wormhole spacetime. They just jump into their respective black holes, and if they meet in the middle, that's an indication that they live in a two-sided wormhole spacetime, two-sided black hole spacetime, right? But the additional claim of Bao and colleagues is that if they do meet, not only is this an indication that they're in a two-sided black hole spacetime, but they can actually determine the type of wormhole under a given classification scheme for wormhole states that we'll discuss in just a minute. And their point here is that this second claim is analogous in the entanglement case to projecting onto a particular entangled state. To prove the second claim, the fact that the claim that two observers can not only determine whether they're in a two-sided black hole spacetime, but go further and determine the type of two-sided black hole they're in, is based on a particular way of categorizing two-sided wormhole states. And this is due to a proposal in Maldacena and Susskind's original article, in which they, according to which they first consider the time-dependent thermal field double state, right? This is from the, recall, this appeared in Maldacena's example of a duality between extended ADS Schwarzschild spacetime and a thermal field double CFT state. Here's the time-dependent version of the thermal field double state, right? It has this time-dependent term. Maldacena and Susskind suggested that we can consider the family of entangled states associated with a time-dependent TFD state literally as a one-parameter family of different entangled states, right? Parameterized by some alpha, as opposed to just a single entangled state that evolves in time. So that's their proposal for interpreting a time-dependent thermal field double state, right? A family of different entangled states. So the next question is, what does this family of different entangled states on the boundary correspond to in the bulk? Well, their proposal was that each member of the family corresponds to a particular bulk region that can be identified with a wormhole unique to that entangled state, right? And so the bulk region they propose is the causal diamond that's anchored at the boundary at a given value of t or alpha, right? So for the t equals 0 member of this family of entangled states, the wormhole in the bulk is represented by this causal diamond, this green region. And for some other member of the family at some value of alpha other than alpha equals 0 or t equals 0, right? The bulk region that represents the corresponding wormhole is given by the causal diamond anchored at that particular value of t on the boundary. right? So this green region. So the idea is here's a way of classifying wormhole states associated with a two-sided black hole, right? In terms of with respect to a single entangled state on the boundary. So each wormhole in the bulk given by this causal diamond green region corresponds to a single entangled state on the boundary. So that's one, right? So that's one way of classifying the wormhole states associated with a two-sided black hole spacetime. And Bao and colleagues then make the following claim. With respect to this classification scheme, it turns out they argue you can actually determine a particular value of alpha, a particular member of this family of entangled states, and hence determine which corresponding wormhole state you're in the bulk. So the claim is we can determine alpha by measuring the tidal force at the intersection in the interior region 2 of time-like geodesics that originate in regions 1 and 4. Right? So intuitively, they correspond to Alice and Bob jumping into their black holes and then meeting in the interior at some point. So let's represent that point of intersection by the coordinates q and 0 for simplicity. And so how do we determine the type of wormhole, given that we know that we're in a two-sided wormhole state? We've met in the middle. The idea is the following. In region 2, Kruskal coordinates satisfy this relation, it turns out. The Kruskal coordinates appropriate to, for instance, extended ADS Schwarzschild spacetime, where recall R sub star is the appropriate tortoise coordinate. It's ultimately a function of R. Now, at the point of intersection, if it's labeled by Q0, then the Kruskal coordinates satisfy this relation, in which the parameter alpha explicitly appears, given that we understand alpha as a measure of the shift in the Kruskal T coordinate. So at step 2, we now have a formula that relates alpha to the radial coordinate R. And now Bao and colleagues observe that well, we can. There's a measurable property of the spacetime that we can also calculate at the point of intersection. It's the tidal force at the point Q0, and it's given by a particular component of this thing called the Weil curvature tensor. And it turns out if you calculate this component of the Weil curvature tensor at a point, it turns out to be a function of the radial coordinate. So the proposal is let's measure the tidal force at the point of intersection. That gives us a value for the Weil, this component of the Weil curvature tensor. We can then solve for R in the formula in step 3, and then use that value of R in the formula in step 2 to get a value of alpha. And in that way, in principle at least, they claim we can determine a value for alpha, and hence, right, what member of what wormhole, two-sided wormhole state we're in terms of this classification of two-sided wormhole states. So that's their proposal, right? Again, to step back, they claim just as entanglement is non-detectable in a certain way, so are wormholes non-detectable in an analogous way. Now, how strong is the analogy? So here are at least 2 disanalogies we should be aware of, right? The first is, in general, entanglement non-detectability seems to be due to nonlinearity, right? The idea that the sum of 2 entangled states need not be an entangled state, and hence any naive operator that represents entanglement cannot be linear. If you might think of this nonlinearity aspect of entanglement as a consequence or related to the fact that entanglement is relative to system decomposition, right? This is the idea that a composite system can be in an entangled state with respect to one way of decomposing it into subsystems, and yet be in a non-entangled state with respect to another way of decomposing it into subsystems. That seems to be related to this non-detectability of entanglement. And the point is that wormhole non-detectability, at least as understood by Bain and colleagues, seems to be due to the local nature of curvature, right? In the case of a single observable, trying to determine whether she's in a one-sided wormhole, black hole spacetime, or a two-sided black hole spacetime, or to a particular way of classifying wormholes, right? This way that proposed by Maldacene and Susskind. And in both cases, it doesn't seem that there's a similar notion of relativity associated with the non-detectability of wormholes, right? So the general question, the relevant question to ask here is, can a spacetime admit a wormhole under one decomposition into subregions, but not another? Right? That would sort of be the dual to this relativity of entanglement to system decomposition. And the point here is that, this analysis of wormhole non-detectability by Bain and colleagues doesn't seem to take that into consideration. Okay, so so far, 3 examples of no-go theorems that seem to be similar in the context of entanglement and in the context of wormholes, and some potential reasons to be concerned with all 3 of these examples. So now I'd like to move on to the third part of the lecture. The third and fourth parts involve stepping back. I'm now considering, regardless of the motivations for ER equals EPR, what are some potential applications we might put it to? And in part 3, I'd like to consider the original application that Maldacene and Susskind put it to, namely as a potential solution to the firewall problem associated with the information loss paradox. So here's one way of characterizing the firewall problem. And here I'm following a critical article by David Wallace from 2020, as well as the review article by Harlow, his Jerusalem lectures on black holes. So the context is the process of black hole evaporation, right? And in particular, we're asked to consider a late stage in that process, a stage in which we can identify 3 modes of radiation, right? There's this mode conventionally called R sub B that's far from the black hole. The black hole literally is this black circle, right? So mode RB is an early stage mode emitted early on in the process that at this late stage is some distance away from the black hole. There's another mode, capital B, call this a late stage radiation mode that's just outside the event horizon. And then there's this interior mode A inside the event horizon. And now we're asked to consider the following 3 claims. And the problem is going to arise that not all 3 of these claims seem to be individually well motivated, but they cannot all be true. So the first claim is the following: for any late stage radiation mode B, just outside the event horizon, there is an early stage mode RB far from the horizon that is maximally entangled with B. And this follows from a statistical mechanical analysis that was performed by Page in this influential article from 93. The second claim is that for any late stage mode B, just outside the horizon, there's an interior mode A that's maximally entangled with it. And this follows from a quantum field theoretic analysis of modes on either side of an event horizon, similar to the analysis that we considered in the context of quantizing a field in a background spacetime. And then finally, the third claim is a statement of monogamy. Right? A system cannot be maximally entangled with two other systems. And the problem is that if the first two claims are true, then B is maximally entangled with two other systems, right? R, B, and A. And the firewall problem is associated with a particular attempt to resolve this, I guess you might call it a trilemma. And this attempt was described in this famous article by Al-Ha'iri and colleagues, Al-Ha'iri, Maroff, Polchinski, and Sully, right? AMPS for short. And their proposal is the following. They suggested we can deny B, claim B, little claim B, by claiming that every late stage mode, capital B, just outside the horizon corresponds to a high energy interior mode, A. And the collection of all such A's forms what they refer to as a firewall. Right? Literally, a collection of high energy modes that you would experience if you jump through an event horizon of a black hole. So that's right. And if there are these high energy states, that effectively severs the entanglement between them and any exterior state B just outside the event horizon. Now this generates what's called the firewall problem because according to general relativity, nothing should happen if an observer goes through the event horizon of a black hole. You should just, there's no drama, quote unquote, right? It's a smooth transition from the exterior region to the interior region. All right. On first glance, right, AMPS's proposal might appear, at least initially, to be a little bit ad hoc, right? Certainly, if there's a firewall just inside the event horizon of a black hole, we can solve this problem with these three incompatible claims. That allows us to deny the second claim, obviously. But is there any justification for the claim that there's a firewall inside the event horizon of a black hole? Right? Is it just an ad hoc way of dealing with this problem? And here's one way of motivating the firewall hypothesis. So we might try to motivate it by deriving this expression. So it turns out if you take the expectation value of the stress energy tensor of a scalar field in a black hole spacetime, with respect to the wedge vacuum, the vacuum that's associated with, right, the wedge representation of the canonical commutations of your field. In the Minkowski context, this was called the Fullen representation, right? Then you can show that this expectation value diverges at the horizon, right? So that's an indication that there's a firewall, there's a divergence in energy with respect to a quantum field at the event horizon of a black hole. But you might be concerned with this way of motivating the firewall hypothesis insofar as, again, it seems to be, it faces this kind of technical issue of unitarily inequivalent representations, right? So it turns out the divergence is derived by expressing the stress energy tensor in field modes that belong to the global representation of the canonical commutations of your field, right? In the Minkowski context, this is the Minkowski representation, and so we're taking the expectation value of an object that belongs to the global representation, and we're taken its expectation value with respect to an object that belongs to the wedge representation. And without further ado, that's a mathematically ill-defined procedure, right? So you can derive a similar divergence in the expectation value of another operator, right? Namely the global total number operator, capital N, with respect to the wedge vacuum. You can show that the number operator associated with the global representation of your field, the expectation value of it with respect to the wedge representation vacuum diverges as you go near the event horizon, and in Minkowski space-time as you go near the Killen horizon, as you approach the Killen horizon. Right? And this is one way of deriving what's in Minkowski space-time is called the Unruh effect. Right? Colloquially, it's the claim that the Minkowski vacuum consists of a sea of Rindler particles. And some philosophers of physics claim that this way of deriving this divergence in the global total number operator is, quote, an artifact of the peculiarity of unitarily inequivalent or even stronger inequivalence disjoint representations, and not a guide to the particle contents of the Minkowski vacuum. Right? So we might make a similar statement with respect to the divergence of the stress energy tensor. Right? Perhaps it's just an artifact of the peculiarity of disjoint representations, unitarily inequivalent representations, and not a guide as to what really happens if you jump into a black hole. In any event, suppose we take the existence of firewalls seriously. Right? Suppose we are convinced by these sorts of derivations that justify the firewall hypothesis. Then if we do, then Maldacena and Susskind propose the following resolution of the firewall problem, ER equals EPR based resolution. And it seems to me that in their article, they present two versions of this ER equals EPR resolution. So I'll call the first version the disruption version. And according to this version, we deny the second claim for a particular late stage radiation mode B, namely that mode B that corresponds to an early stage mode RB that has been distilled by an infallen observer. So their concern is with an observer who is fallen towards the black hole, who distills RB, and then continues her journey, compares RB with B at the event horizon, right? Determines that they're maximally entangled, and then falls through the event horizon, and then compares the result with A, right? Again, the concern is this violation of monogamy. In that context, right, Maldacena and Susskind suggest, well, the act of distillation at RB disrupts, quote unquote, the entanglement between A and B. How does it disrupt this entanglement? Well, the claim is that there's a wormhole that connects A and RB. And this is the conduit through which distillation at RB disrupts the entanglement, right? Literally, distillation at RB produces a high energy mode at A, and that disrupts the entanglement between A and B. That process leaves all other interior modes entangled with their corresponding late stage exterior modes, right? There's only a single disruption in the entanglement in this particular case. So they say, quote, in our view, the particle A was created at the other end of the ER bridge when Alice, the infallen observer, distilled RB. So in this disruption version of the ER equals EPR resolution, for an infallen observer who has distilled RB, there is an exterior mode B and a single high energy interior mode A, such that B is maximally entangled with RB, right? That's the consequence of Page's analysis. That's the first claim in the yellow box. And RB and A are connected by a wormhole. Right, that's the conduit of disruption. But this is slightly puzzling, right? So this way of resolving the firewall problem via ER equals EPR, at least on the surface, suggests that RB and A are entangled. Right? If we're assuming that there's a wormhole between RB and A that allows something you do to RB to disrupt A under ER equals EPR, shouldn't that entail that RB and A are entangled? And now the threat of monogamy arises again in this context, not for the mode B, but now for the mode RB. Right? Now there's a risk that RB is entangled, maximally entangled with two other modes, B and A. So this is the disruption version of the ER equals EPR resolution. But there's another version of the ER equals EPR resolution that Maldacena and Susskind discuss in their article 2. And this version has come to be called A equals RB. So the claim here is that there is a wormhole connecting RB and A, and that this underwrites an equivalence between RB and A. Right, and so this allows us to resolve the conflict between these three claims in the yellow box, to the extent that we can now say B is not entangled with two other subsystems, rather it's just entangled with a single system, namely the system A/RB. And their equivalence, again, under ER equals EPR is justified by, supposedly, by the existence of a wormhole that connects them. Now, here's one way that Maldacena and Susskind describe this second version of the ER equals EPR resolution. So the diagram on the left is a conformal diagram of extended ADS Schwarzschild spacetime. The modes A and B are represented in the upper right-hand corner, and the assumption is B is close enough to the boundary to be considered as a subsystem in the boundary CFT. And under Maldacena's duality entry in the ADS CFT dictionary, we can claim that a B, there's a mode, call it A prime, that's a subsystem of another copy of the CFT associated with the left boundary, such that B and AB are the two subsystems in a thermal field double state, boundary double state. Right? So that justifies claiming B and A prime are entangled with each other, maximally entangled in the thermal field double state. And there's yet a fourth mode identified in this diagram, A double prime, that's assumed to be on the same spatial slice as A, and obtained from A prime by time evolving A prime on the boundary. Right? So we time evolve A prime to the point where we get a mode that's on the same spatial slice as A. And now A double prime is understood to be to correspond to a late stage radiation mode RB. And so in this context, we can say A double prime and A are connected by a wormhole insofar as they are on the same spatial slice of extended ADS Schwarzschild spacetime. And the sense in which that wormhole underwrites the equivalence, the equivalence between A and A double prime the suggestion by Maldacene and Susskind is that perhaps we can identify A double prime as a boundary representation of A, perhaps in the context of the ADS Rinder representation. So that's one way they attempt to justify this second ER equals EPR resolution in terms of this A equals RB interpretation. So one slight puzzle with this resolution is the sense in which wormhole connectivity is supposed to underwrite equality or equivalence, right? If we assume a wormhole that connects A and RB, A and A double prime in the diagram, in what sense does that underwrite the claim that A and A double prime or A and RB are identical? Okay, so two versions of the ER equals EPR proposal to resolve the firewall paradox. I mean, one observation here is that these different versions are distinct, right? The disruption version denies the second claim in the yellow box, whereas the A equals RB version accepts the second claim. Okay. So let's now move on to the last part of the lecture. This is a potential second application of ER equals EPR as a potential causal explanation of entanglement correlations. So the question here is, does the presence of a wormhole connect in two regions that support observables that exhibit an entanglement correlation causally explain the entanglement correlation? And this question might be of interest, right, to somebody who understands an entanglement correlation in the following way. So let AB be a bipartite system in an entangled state with subsystems A and B localized in spatio-temporal regions X and Y. Then observables OX and OY associated with A and B can be said to exhibit an entanglement correlation just when the following three conditions hold. They're correlated. The distance between their regions of support exceeds an appropriate bound on causal signal propagation. Right? And this suggests that their correlation cannot be explained in terms of a causal signal that could propagate between them. And finally, there's no random variable lambda such that OX and OY are conditionally statistically independent with respect to lambda. That's an ingredient in the derivation of a Bell inequality, right? And that might be interpreted as entailing that there's no common cause explanation of the correlation between the two observables. Right. So here's a way of interpreting entanglement correlation as a correlation that does not admit a causal explanation, either in terms of a direct cause or a common cause. So then let's now suppose these two regions X and Y are connected by a wormhole. Suppose ER equals EPR is true, right? So if the systems are entangled, then that means the regions of their support are connected by a wormhole. And now there are two questions, right? Can condition D provide the missing direct cause explanation of the correlation? And secondly, can it provide the missing common cause explanation of the correlation? So the answer to the first question seems fairly straightforward, right? Can a wormhole provide the missing direct cause explanation of an entanglement correlation? And arguably the answer to this is no, right? Here's the relevant setup. We have our two regions X and Y. They're separated, they're space-like separated, right? So no causal signal can travel from one to the other in the exterior space-time. And then the question is, does the existence of a wormhole that connects them allow them to send a causal signal, allow them to be connected by a causal curve. And as we've seen, the answer to this, is there a causal curve between regions X and Y through the wormhole? Not for typical general relativistic spacetimes, in particular spacetimes that satisfy the average null energy condition. So wormhole connectivity arguably cannot provide a missing direct cause explanation of entanglement correlations. What about a common cause explanation? Can a wormhole provide the missing common cause explanation of an entanglement correlation? And here we might distinguish between two senses of common cause. We might say that observables OX and OY share a statistical common cause just when there's no random variable that screens one off from the other. And we might say two spatiotemporal regions XY share a spatiotemporal common cause just when they share a common past. And how you define the notion of a common past turns out is a matter of, well, there are a lot of different options for such a definition. And some of these were discussed in an article by Jeremy Butterfield a while ago. Right, so here are three suggestions for the notion of a common past of two regions X, Y. Right, one popular definition is just in terms of the intersection of the causal paths of regions X and Y, right, which would be this triangular region here. But the point here is that you can adopt other candidates too for the common past of two regions X, Y. And this suggests, right, this mysterious nature of entanglement might be understood in terms of this kind of separation between these two notions of common cause. Right? Entanglement correlated observables lack a statistical common cause, even when their regions of support may share spatiotemporal common cause. It just depends on the definition of common past you adopt. Let's modify our question slightly. Can ER equals EPR provide the missing link between statistical and spatiotemporal senses of common cause? In other words, is the lack of a statistical common cause exhibited by entangled observables mirrored by the lack of a spatiotemporal common cause for wormhole connected regions of support X and Y? And the short answer to this question is you can always contrive a situation in which the answer to the question is yes, right? So in certain constrained scenarios, wormhole connected regions can be thought of as lacking a spatiotemporal common cause for an appropriate definition of common past. Sorry. So here's one contrived example. Here's truncated extended ADS Schwarzschild spacetime and two regions XY, right? In the two, so it's truncated along the t=0 spatial slice. And two regions X and Y in the two exterior regions, and they're localized in the exterior regions in such a way that they do not have a common past, at least under the first definition of common past. Right? There's no intersection of their causal paths. And if ER equals EPR is true, then observables localized in X and Y potentially exhibit an entanglement correlation, and that's mirrored by the lack of a common past due to the particular features of this wormhole spacetime. The relevant question here is, are the bulk regions XY that do not share a common causal path dual to boundary regions that support entangled boundary observables? So for contrived examples, right, we can provide a missing link between statistical and spatiotemporal senses of common cause in terms of ER equals EPR. But the question is, does this hold for more general scenarios? And so my assessment is probably not, given the contrived nature of the examples. Okay, so that's all I wanted to say about ER, because EPR is a potential applied to the context of providing a causal explanation of entanglement correlations. So I think I'll stop here.
Thanks a lot, John. So I think we're perfectly on time. We have maybe time for a couple of quick questions. I see that Enzo has raised his hand. So Enzo, please, you can go.
Thank you very much, Jonathan. Thank you for this last lecture that was especially interesting and intriguing on problem up to date in foundation of physics, explained in a very clear way. I hope that next time you will be with us in Urbino, in actually, not only virtually. And I have a very general question. In the last years, Pennington and other guys realized calculation that show that it is possible to. I have problem with my. Can you hear me?
Yes. Mm-hmm.
Yes. In last time, Pennington and other guys, Harlow, Maldacena, and many, realized a calculation that seems to the island calculation that seems that it is possible to avoid firewall. And Marco and Enrico wrote a paper that I don't know where it appeared in Synthèse. Perhaps Enrico, I don't remember. It seems to me in Synthèse. In this paper, they propose that in a certain sense, in this calculation is assumed that the two particles that in EPR second solution are connected by a wormhole, in a certain sense, are the same system. It is not possible to distinguish between these two particles because the algebra observables relative to these two particles does not commute. So in a certain sense, they are the same object. And since this, I am not able to evaluate really this proposal, even if it seems very interesting. And my question is, it is possible that you answer in the negative to the possibility that the wormhole in EPR hypothesis can, in a certain sense, satisfy our desire that Bell correlation be, in a certain sense, at least partially causal. But perhaps if there is something similar in new calculation of the relation between what happened in the bulk and what happened in the boundary in the future, we can find something similar in the sense that even for, in general, for each kind of, this is very speculative, for each kind of EPR correlation, in a certain sense, we are in the entanglement in the boundary. We have in the bulk a situation similar to what happened in the case of island calculation. That is, the algebra of observables do not commute, and so in a certain sense the system is only one. And in this sense, even if there is no causal explanation, there is an ontology a bit more palatable. I don't know, perhaps it is completely full what I am saying. Thank you very much again.
Oh, yeah, thank you for those comments. Yeah, I'm aware of those papers by Pennington and colleagues on the East Coast and the West Coast. But I'm not, I don't understand all the details. I'm not exactly sure, but so they are supported in this particular type of resolution, this general A equals RB way of resolving the firewall paradox, I assume. Yeah, I haven't attempted to look at any of those more recent articles yet.
Yeah, yes, Marco Enrico attempt to show that yes, there was inside this paper there is Enrico can explain better than me. Perhaps Enrico, can you say something about this topic better than me? Thank you.
Sorry, about what? So about
Sorry?
No.
Yeah, about your paper on Pennington and co calculation and ontological assumptions that could avoid. Could be the reason because we do not need the firewall.
Oh yes, no, I mean it's something that is already in the paper by Maldacena and Saskin. So it's really just this thing here. It's just that what they show is that the A double prime and A modes have a non-zero commutator. So since they have a non-zero commutator, they're not independent degrees of freedom, and this is why they say that they're equivalent. That is the trick that they use. But of course, it leaves open the question as to how exactly like a wormhole does mediate this equivalence. So I mean, yes, I mean that's the point. Yes.
Yeah, and I think it's the case that in the original, in the Maldacena and Susskind article, they motivate the equivalence by appealing to boundary reconstruction. Right? That in some sense A double prime can be thought of as an ADS random representation of this bulk observable inside the event horizon of a bulk black hole. But so I take it there's another way of establishing equivalence too, in terms of non-commuting algebras of observables that the A and A double prime mode belong to.